Hi, everybody. Welcome back to the second video in cluster analysis and cluster analysis heat maps for the data science methods for digital learning platforms. So in this second video, we'll be talking about building on what we talked about in the first video with the example from my 2010 paper for cluster analysis heat maps, but starting to get into the specifics on what are these methods and what is cluster analysis and how does it work and how do we begin to use it? So what is cluster analysis and what are cluster analysis heat maps and what are the recommendations? It's a video on top of that. So let's just have a definition, cluster analysis. So this relates back to the definition that we had from Weinstein in the last video. But I want to go into this definition deeper. Because I think it's a really useful definition that lays out some of the reasoning that I've been talking about across the slides in the last video. So Weinstein says, for a visualization, by far the most popular graphical representation has been the clustered heat map, which compacts large amounts of information into a small space to bring out coherent patterns in the data. In the case of gene expression data, which a lot of this work is from bioinformatics, in the early 2000s. So that's why they're talking about gene expression data. The color assigned to a point in the heat map grid indicates how much of a particular RNA or protein is expressed in a given sample. The gene expression level is generally indicated by red for high expression and either green or blue for low expression. Let me repeat that. The gene expression level is generally indicated by red for a high expression, either green or blue for low expression. So again, it's a heat map. So red is high, blue is low. Coherent patterns, patches of color, are generated by hierarchical clustering on both horizontal and vertical axes to bring together like with like. Cluster relationships are indicated by tree-like structures adjacent to the heat map. And the patches of color may indicate functional relationships among genes and sample sources of order other than clustering, for example, in a time series of measurements. So you saw that by x-axis in the 2010 paper. I ordered the x-axis by time and then by core subjects. I could just as easily have clustered both the rows and the columns. And I'll show you an example of that coming up in a future video. So cluster heat maps have a long history in data visualization research. So I just want to show this example from Wilkinson and Friendly from 2009, where they talk about Wilkinson's cluster heat map from 1994. In which Wilkinson was using global data, such as across countries, including urbanicity, overall literacy, citizen life expectancy, GDP per capita, health, and whatnot, to cluster by countries across like OECD or UN level data. You can see that there is here in this cluster analysis in 1994, it's a cluster analysis heat map showing really strong clusters that basically cluster and pattern the world into the OECD countries and then the non-OECD countries. And also here is it's an example of clustering on both the rows and the columns. So you can see that like the last four columns are like mortality indices. So those columns are the kind of the opposite kind of data. So the richer, more historically advantaged countries have lower mortality issues than the countries that are down in the bottom cluster. And of course, this is 1994. Things have changed quite radically for many of these countries, which is nice. So, but Weinstein in this piece also says that cluster analysis has its limitations. So I want to talk through some of these limitations because throughout these videos in this section of the data science class, I'm a proponent, obviously, of cluster analysis heat maps. I use them all the time in my research. I think they're really great. They're hot, if I can make that joke. But this idea that they're the cure-all and that they're amazing all the time, there's a lot of problems as well. And we got to think about their limitations as we use them. So as Weinstein says, seductive though it may be, the clustered heat map has its limitations and potential for misinterpretation and misuse. So, number one, most prominently among the limitations, it provides only first-order insights into the data. Complex nonlinear relationships among only a few of the samples are unlikely to show up. So if you've got really weird data and nonlinear data in which those weird nonlinear relationships are happening for just a few of the rows, you're not, that's the cluster analysis probably isn't what you're looking for. But that said, you can have really quite weird data, and the patterns, cluster analysis will show many of the patterns. Number two, in hierarchical clustering, each bifurcation of the cluster tree can be swung in either direction at each fork in the tree. So some objective, but to a degree arbitrary rule must be invoked to decide which way each branch will in fact swing. So we need to be really clear in our methods what we're doing, because there's a lot of arbitrary decisions when it comes to doing cluster analysis. Because again, it is a descriptive statistic. Number three, there's also the temptation to select a small subset of the variables and represent them in a clustered heat map. However, if one picks a signature consisting of only a few dozen features or variables out of a set of more than 10,000, then even randomized data can produce clustered heat maps that appear spuriously to show good distinction to subclasses. So this means use all your data, use all the variables. So you may be thinking, well, just use the ones that I think are most important. No, use them all. Why? Because of this problem. So one of the great things about cluster analysis, and especially cluster analysis heat maps, is that we can see inside your data. We can see every single data point. And so why not include everything and show us what the data looks like inside your data set, and do the pattern analytics with the clustering and show us how this looks and how it works and across all of your really weird variables. If you cherry pick based on your a priori notions, then it's as bad as p-hacking and harking, in which you're just biasing the result based on your a priori hypothesis. Rather, let's do science, and let's instead have all the data and be empirical and have some hypotheses, sure, but we also need to be able to be wrong, and we need to allow the patterns to emerge and come up from the bottom up. So, and additionally, as Weinstein says, even beyond those limitations and concerns, the generation of clustered heat maps is a surprisingly subtle process, and I agree with this. So again, for number one, we really need to make sure that cluster heat maps they're best for comprehensive, feature-rich description. That's what we should be using them. For number two, again, the clustered heat maps involve a long list of arbitrary decisions. So in your methods, just be really clear about what you did. And as you'll see in these videos, my current recommendation is that in your papers, just give us the full R markdown of what you did, in which it provides both the R markdown, like in an HTML that you can just send to somebody or just attach to your paper or post on your institution's Creative Commons open access institutional repository or our GitHub. But show your work. And also don't just give us like an RMD or just the code, because who knows what's going to happen to the packages, 10 years from now. Everything, but when our updates, things can break, as well as, if we were talking about Python or any of the other large scale coding packages and environments. So instead, Markdown is absolutely amazing, in which you provide the code and every table and figure for what you've done. So we've got it all in one interoperable package that you can just send to somebody, or they can just download and see everything all locked in place with the code and the outputs. And so if you have in your methods for your paper or your analysis what you did, and then in your Markdown, you talk it through and have the code and have the tables and figures, then everything will be there, and anybody else can come along and replicate what you did, or see if they can. And that's awesome, and what we should strive to do. And then number three, if you don't use all your variables that you've got and you cherry pick features, variables and individuals to include, this is just going to lead to spurious biased results, just like if you did the same thing in inferential statistics. So please don't do that. So let's talk about cluster analysis, heat map, distance, and agglomeration methods. So all the fancy model variations that will lead to the exact same inference, me trying to choose. So I start here to say it might feel at the beginning like this when you start into hierarchical cluster analysis, that it all seems like fancy model variations that all lead to the same thing. But I'll just give a warning that from here on out, you're going to get very different outcomes depending on the long list of arbitrary choices that we were just talking about for Weinstein. So please be very specific in your research. You're not going to get just all Pikachus when you choose. You're going to get very different kinds of outcomes given how you set things up. So this is an overall structure slide. I'm going to talk through each of the major issues, as well as move my video pane just a bit so you can actually read my slides. So there's multiple types of clustering. So let's talk through a few. There's a lot. And in the readings, there's a lot more. There's like a new one every week, it seems. And they just keep popping up. So what I like to focus on to start with is the top two, which are hierarchical, so bottom up clustering, in which we consider that first, every row in our data is a cluster. And then as you saw in the previous video, in the 2010 paper, we then agglomerate together these clusters. So you put like with like, the closest patterned data becomes a cluster. And then that cluster then agglomerates and rolls up with the one who's closest to that and closest to that. Now, there's another kind where, which is has a lot of popularity, k-means. And k-means is fairly top-down, in which you identify clusters a priori, really. And you say, I want 3 clusters, I want 4 clusters, I want 5 clusters. And then the algorithm just does what you say and fits that many clusters on top of your data and puts everybody in those clusters. Now, there's some problems with that, in that, sure, if you think there's 3 clusters, you can get back 3 clusters, but that can really bias your results. On top of that, sure, there's like elbow methods that look a lot like factor analysis, where you have like a scree plot. You're looking for the elbow and some fit stat. And that's fine, but you're still eyeballing it. There's no significance, good significance tests. And k-means is somewhat arbitrary. I mean, you have to, with k-means, if you want to replicate it, even one run to the next, you need to set the random seed to something that's not random, that's the same every time. Because k-means can come out with different outcomes if it doesn't have a seed to follow, because it's going to set its own random seed every time otherwise. And so the difference, so like, but if you do hierarchical, you'll get the same outcome each time. And so like you'll see across the bioinformatics literature, which I'm drawing a lot of this research from, where they've done tens of thousands of papers across genes and disease types and many different really, really interesting applications. Most of those papers use hierarchical cluster analysis for exactly these reasons, because it's replicatable and really defensible. And you get really informative clusters, as we show. I'm not saying that k-means is terrible. I'm just saying that it's really biased based on a bunch of arbitrary decisions. And there's no clear way of knowing that you've got the right number of clusters, that there's a statistically significant number of clusters. So there's a lot of other clustering algorithms as well. Dynamic EM algorithms, they're distribution-based, spectral density, graph-based. I think my favorite named one is self-organizing maps, which is just a great name for an algorithm. And so, yeah, like in some of the readings, you can really go deep into a lot of these different algorithms. In bioinformatics, there's a ton of research, but across multiple industries, there's a lot of research. My encouragement to you is to use hierarchical cluster analysis heat maps, especially when you're starting out in this area, and then work up from there. They'll give you really strong solutions, and they are explainable really easily. If you start getting into some of these other ones, it becomes unexplainable very, very quickly. And from like a business solution standpoint, or being able to explain it to educators, it gets tough. And on top of it, like I've been saying, like some of the top end, highest level bioinformatics work with clustering uses hierarchical clustering, as I will demonstrate for you and teach you how to do. So I would say start there. There's no reason to be fancy. So again, all of these are descriptive statistics. All of these. There's no hypothesis test. And there's, again, no agreed upon standard way of deciding how many clusters are the right number of clusters. So there's a difference as well between empirical clustering based on distance measures versus like machine learned or trained on a type or a profile. So like cluster analysis is very different from something like a classifier, which like k nearest neighbors, where you classify or recommend. We're just in cluster analysis, we're really just trying to find coherent patterns and be able to talk about them. So also, most clustering methods have big problems with missing data. So watch out. If you have any missing data, k-means is just not going to work for you either. K-means has big problems with missing data. So watch out for that. But one of the reasons I also like hierarchical cluster analysis for education is that when you combine it with the agglomeration method of average linkage, I'll show you how to do, it's robust to missing data. So because it takes the average, and so it kind of just skips over where you've got missing data. I mean, you can't have 100% missing data of a row. It has no idea where to put it. But if it's got some information, then it'll figure out where that row of data should go. So clustering has two major parts. First, you need to calculate a distance matrix. So usually Euclidean distance, the Pythagorean theorem, the shortest distance between 2 points, is used to start with, which is what I'll show you to begin with, the Euclidean distance. But there's many others. And I'm going to show you that I recommend uncentered correlation for education data for a couple different reasons. I'll show you how to do that. And then you need to, once you have your distance matrix, so you know the distance in your hyperdimensional data space from every point to every other point, then you need an agglomeration algorithm. Like, how do you decide which ones are most similar to each other? And I like average linkage because of the robustness to missingness, but there's a ton of other choices that you can make as well. And I'll show you how to find those. So, starting on the left, you might have your novel research idea where you're like, oh, hey, there's a place where I can park here. And as you pull up to that parking lot, you can see some guy in the 1980s, and then you republish the idea, but with deep learning. Deep learning supercut on top of this little other car from the 1980s. So here's the guy from the 1980s, Ramsberg, 1984. This is one of the best books on cluster analysis that I like. It just walks you through in very plain language. If you're going to do cluster analysis deeper in your own work, I highly recommend getting this book from the library. It's up here on my shelf. Also, the Shu and Wunschitz paper is awesome from 2005. It walks through all of the different kinds of distance metrics as well as agglomeration algorithms. And so like you can see, like Euclidean distance is just one of many, many different kinds of ways of calculating distance. So you can calculate distance as the hypotenuse of the triangle, city block distance or Manhattan distance. Like I'm at Teachers College in New York City, so I live in Manhattan. And Manhattan has its blocks, its city blocks are long, east-west, and short, north-south. So like city block distance, Manhattan distance is actually you go long and then short, and then long and then short. And you step to it across instead of a straight line. Sometimes that works better. Mahabalowicz distance, Pearson correlation, cosine similarity, which we'll talk about in a few minutes. These are all really quite interesting, and there's a lot of them. I provide this reading so that you can make an informative choice. I would say start with Euclidean distance, and then I'm going to give one option in these videos of cosine angle and cosine similarity of what that looks like. So my recommendations for cluster analysis heat maps. So first, number one, decide what are the rows. Are they going to be students? What are the columns? Are they features or variables? Do you want to cluster just the rows or just the columns? Perhaps both. But also note that for columns, time is a valid order. So you can see a lot of my examples from my papers use time on x-axis. So I don't cluster the x-axis. I only cluster rows, so people. Decide what should be patterned versus what are the annotations. And I'll show you how to do annotations. So like the annotations in the example from 2010 were like dropout and whether or not they took the ACT. Again, annotations are going to be outside the clustering algorithm. They're just there to see what the relationships with the patterns are. And so decide what's going to be inside versus outside. So what are your covariates? Like gender or sex, treatment, SES, classroom, distals, course completions, grades, graduation. Remember, don't put dropout in the pattern analysis to predict dropout. As we all know, in trying to make machine learning predictions, putting your outcome in as a predictor is usually seen as bad practice for a variety of really good reasons. So please don't do that. So be really cautious about thinking about what should be an indicator. What are you patterning versus what are the relationships that you want to see outside of those patterns. Number three, as we talked about before, include all of the features and data that are relevant. This is a descriptive statistic. Please don't cherry pick. So from genomics, they include every gene they have across tens of thousands by thousands of patients. The more, the better. Again, for the color map, for the heat map, blue is low, red is high. Again, please, you might think that you have a better idea. I've seen a lot of people, you can hear me talking about it quite a bit. I see a lot of people come by, but please follow the standard practice from bioinformatics, as you can see from Weinstein's quote. Blue is low and red is high. And please also do this for colorblind people. As you can see, the Ishihara colorblind test here on the side with the circles with the little dots in them, those all look the same to me. I'm red-green colorblind, and so please don't use green and red together ever in any of your data visualizations as you make them not accessible to colorblind people such as myself. So clustering algorithms. Number 5, choose whether or not you're going to use something like hierarchical or k-means. But maybe you want something else. So, look at bioinformatics literature if you're going to branch out, see, because you're using cluster trees. So you're going to branch out. Anyway, number 6, pick your distance metric. So Euclidean is a good place to start, the shortest distance between 2 points in a multidimensional feature space. But if you think about uncentered correlation or the cosine angle, which is nice. So it's well, you may or may not have seen when you first studied statistics and the Pearson product moment correlation. When you have two vectors that are correlated with each other, that correlation is not similar to, not like, it is mathematically the same as the cosine angle between the two vectors. If you take the cosine angle between two vectors in a hyperdimensional data space, that is the Pearson product moment correlation. They're the same thing. And so what's super cool about that is if you use uncentered correlation, this cosine angle, what you get is if you use Euclidean distance, it's very difficult to be able to see the difference between two lines that, like here on the right, where you can see that there's two lines that go up and down at the same rates, perhaps, but they're separated by some metric distance, but they're separated by the same amount. What uncentered correlation will do is it'll show these two as being a little different from each other versus Euclidean, where they'll be very super similar to each other. And so I like uncentered correlation because it gives more distinctive clusters, especially when it comes to this kind of data. It works better when you want to see these differences when you just have a metric distance between like a student who's a high-graded student who goes up and down at the same, and the low-graded student goes up and down, but they're very, very different students. And uncentered correlation will do a better job of revealing those patterns than Euclidean. Agglomeration method, I'll show you in a moment. The average linkage is, so I like to use average linkage since it's, as I've said, robust to missing data. It gives really good results, but there's a lot of other ones. Complex is one of the defaults in a lot of places, but we can, but I'm going to talk through average linkage, and it's then up to you if you want to go look for someone else. So you might be saying to yourself, hey, I'm a data scientist. I know some machine learning and also maybe some stats, maybe even some psychometrics. And, tell the difference in the clusters. What does Bowers know? I'll just use, I want to know which clusters are the right clusters. And I want to tell the difference. So I'm just going to use PCA or TSNE or something statsy or deep learning. They'll tell me which clusters are real. Well, I'll just say again, that the bioinformatics literature on exactly this question is vast and remains an open question to this day. Good reading before you go too far down that rabbit hole is Quackenbush's 2006 piece. It's great on exactly this issue, and get the cited bys on it. You'll see people are still arguing over all of this. So I like to think about, use cluster analysis heat maps to describe your data. It's like a much better and comprehensive table 1 in your paper for descriptive statistics on your features, because it shows all the data and all the relationships for every single individual across all your variables. No averages. It's all there for people to take a look at. It's great. So let's talk through an example. So this is from Romsberg, the 1984 book. And so I'm just going to show an example using student grades with Euclidean distance and average linkage, just to walk you through what the math looks like, arithmetic really, and what it looks like in 2 dimensions. So here at the bottom, let's go back to this idea that we've got 5 students and the student IDs, 1, 2, 3, 4, 5. And each of them have a grade in English and in mathematics. And we want to cluster these students together using hierarchical cluster analysis, using Euclidean distance and average linkage to see, what do we have? What are the patterns that we have? And so, this is pretty reasonable data, right? We've got some students getting high grades, others low. Let's see what these clusters look like. So we have 2 dimensions of data, English grades and math grades. So let's put English grades on the x-axis and math grades on the y. And so now we've got each student in 2 dimensions. And we'll keep it to 2 dimensions so that we can visualize it. But the arithmetic and the algebra all work great in hyperdimensional spaces when you have 10,000 dimensions. So, but we'll keep it in 2 just to make it reasonable so we can visualize it. So you can see student 1, 5, 2, 4, 3. Like student 1 is getting a D in both. So they're at 1.11, right? So we've got the data in the data space. Okay. So the first thing we're going to do is calculate the Euclidean distance, the hypotenuse of the triangles in the data metric of the data space. So here again, we've got grades data. So they go from 0 to 4 in both dimensions. And so we're just looking at and calculating the distances between every single point. And so this is the Euclidean distance. And so you can see that the difference between student 1 and student 5 in this space is a 1 grade point, right? They got the same grade in English, but student 5 got a 2.0 in mathematics. So they're a 1. So you can see in the correlation or the distance matrix down here, this is a distance matrix at the very bottom, that's 1.0, right? So wait, there's a 3.0. The student 3 versus student 5. 3, 5, 3. They got a 4 in English, and student 5. So 3 and 5 are kind of the opposite of 1 and 2, right there. 3 and 5 got the same math but different English, and so they got 3. And so like the difference between the distance though, when you've got across this data space, difference between 1 and 2, well, difference between 1 and 2 is 4.01 grade unit points in this data space. So notice we need all of the variables on the same unit measure, which I'll talk about in a little bit. One of the things, if your variables are all on the same unit measure, so let's say they're not all grades, on a 0 to 4 point scale. You would then want to z-score them all, put them all on the same scale, because otherwise one dimension will pull all of your data towards it just because the numbers are bigger. And I'll show that example in a future. So here, this is the first step. We've got Euclidean distances between everybody with everybody in this two-dimensional space. Now we're going to use average linkage. It's the distance between any two clusters as defined as the average distance of the total number of cases within both clusters. So let's look at what the math looks like. So we take the so what you do with the agglomeration is the algorithm will say, okay, who are the closest 2 points? Well, we know who the closest 2 points are. Let me go back one slide. If we go back one slide, let's just look at this distance matrix. What's the smallest number? Well, it's the distance between student 3 and student 4, right? 3, 4. They're closest. You can see it right here. So if we go forward a slide, so student 3, 4 are the closest. So we're going to take the average between them, student 3, 4, and then update the distance matrix. So we're going to now have the distances between the average between 3, 4, cluster 3, 4, and everyone else. So now we've got a distance between, because every single person is their own clusters, and when you start off in hierarchical cluster analysis, so we look at the distance between cluster 1, 2, 5, and 3, 4, and now we just continue to do this. Who's next closest to each other, and we update the distance matrix. So now we look at cluster, who's closest next? Well, 1 and 5. And then but keeping 3, 4. So now we update the distance matrix, and we do it one more time. But now we bring cluster 3, 4, and 2 together. And what's interesting on the left are those distance matrix tables that I just talked about using Euclidean distance and average linkage. What the cluster tree, this dendrogram, does is, again, longer lines indicate more dissimilarity. So when the unit space that your data set is in is all the same, whether it's z-scores or here it's in grade points, you can see that, again, remember that 1 and 5 were 1 grade point away from each other. Well, that's exactly what the cluster tree will show, because 1 and 5 were 1 grade point away from each other. Remember, cluster 3 and 4 were like 0.3. And so that's about a 0.3. And then as you agglomerate and go up the tree, the cluster tree literally represents on its x-axis the data space in Euclidean distance between every single cluster at both the row level and as you agglomerate up, so that the cluster tree represents showing your work. It shows the pattern analysis in the unit metric of the space of your rows. And it's really quite intuitive once you begin to do it by hand like this, and you can see how the dendrogram is created. And so then after that, we just put the heat map on it, where again, hot is high is hot A, and so that's going to be a red, and blue is cold. And so we could just then put a 2-column heat map on this. Here I've made gray the middle of the scale, and then you can put some set of annotations like whether or not the students graduated. And so that's how you do Euclidean distance and average linkage. Coming up next in the next video, we'll be talking about some examples from the research literature. So I'll see you in the next video. Thanks so much.